So the first thing, this was probably the program with the normal implementation with the nth root, right, and the one that creates the table. So if I compile I can't type. If I run this, this is the table generated automatically, right? That's the stuff you'd have to do by hand, but you notice that's great now. Any code that uses that table is indeed one assembly level instruction to do it, which is kind of really neat. Now let's go take a look at this what? Where did I keep the const exp? It's already in that one, but I don't want to show you this. So let's load this up. S2 LRGB CPP. So this one, as you notice, that's the one that creates the table, right? Everything is tagged const exp. Okay, except this guy that's not. At the moment, it's a traditional function, but the other ones, the nth root, the myabs, and the pow are all const exp. Okay, so that's exactly the same as on the slide, except for this guy, which is not. Okay, so now if I have, and I have, of course, the printout. So I just wanted to actually show you this little thing. I'm going to repeat the trick I've used before. Dash S dash dash or single dash emit LLVM plus plus 14 minus O foo.ll. Okay, Emacs no window foo.ll. Come on. So that's the assembly. You see here, the function is actually here, define float real linear to sRGB, so I still have a function. And you see that it has these labels that correspond to the branching in the function. So you have this part, which is basically loading, doing a multiplication and a store. That's the case that corresponds when you're smaller than a specific constant. This hexadecimal number here, right, that thing, is the constant you find. Let me load the code at the same time. S2 LRGB.cpp. That's basically the test that you have here, right? So this constant 0031 in hexadecimal, this is because it's represented in hexa, that's what you see. And here the first branch is the base case. The other one is this part, right? So you see that the function is here. You have this case, you have the other case, and you see the computation going on, calling IPO FI and whatnot, and nth root, etc., etc. Okay? Make sense? So the entire thing is present. You have all the function as normal. Why is that? Well, remember here that the function here is still a normal real linear to sRGB, right? Because I didn't tag this guy const exp. That's what I need to do. If that guy is constant, then now the program could be unrolled and called with different value of real linear to sRGB. Okay, so let's simplify the printout here just a little bit so that it's not too overwhelming looking at the assembly. But I'm going to say float x equal, and I'm going to just call that guy for a specific entry. Like, for example, the last entry. Okay, so I do that, I hard code this so that I have a very simple assembly to look at so that we don't get lost in the assembly. Now I go back, compile this guy, go back, load foo.ll. Yes, let's reload. Now you find main, and he still has the call, okay? So you see that's why you have to be careful. We still have the call here, and it's kind of obvious. He's really calling the function. So he didn't quite do what I wanted to. I didn't get, so we get back to revisit your question. We didn't quite get what we want. He didn't generate the code really at compile time. right? I would have expected here to have the result of the computation, but I don't have. I have a call to the function, and the function is underneath in all its glory with all the ugly details, okay? So that's fine. So let's fix this. We have to have a const. We have to make this const.
That changes whether or not it compiles.
Well, we'll see, right? That's the whole idea. It should. The point is that it should. Because I'm never... okay, so that's going to be annoying here because I'm decreasing E in place. Let's try without a const on this one. Okay. No. It's foo. Still not doing it. Okay. What is going on here? Const text float. Yeah, I'm sending in the right place and I'm compiling the right file. Ah, finally. Gone. Okay. So what is the change? So I stuck a const exp here. Otherwise, it was basically saying, oh yeah, you're storing this, but x is a variable, so I don't have any reason to do that, right? I just removed that guy, changed nothing else,
So
recompile, go back, load. I'll be with you in a second, Brandon. And again, here, if I go, now you see that my main contains temporary 7 is the result of calling read linear to sRGB with that specific input. Because I didn't tag that expression, that assignment needs to be const, right? That's the important part. I need to say you are const here. And if I do that, then it cleans up, right? Again, doing it, going back, reload. And now you see that he indeed stored, and that hexadecimal value is really the result of the call. So this time he did evaluate. Okay? We good? You see that I'm looking at the assembly to show for real, right? That it matters. Now the last thing I want to check, because I really had a feeling it didn't matter, I added these const. I don't think that they're necessary, so I want to check. Because what matters is that the expression normally is constant. Okay, so now it's only this one, right? I missed one const. Oh, yeah, you're right. Okay, good. We're good. We're good. Let's do this again. Foreground, foo.ll. Yes. Go to the top, and it worked. So indeed, the const inside on the argument do not matter. But as you've seen, don't deceive yourself. You're missing a single const exp at the right spot, and he generated a call to the function at runtime, rather than evaluating at compile time and sticking in the value. Yes, Oliver?
Is there a way to make it at least one when it does that, or no?
No. You know how to use a MIT LLVM? You know how to read assembly? Go for it. Brandon, you had a question.
could the constant value have been like inside the call to the function somehow earlier?
Can you just tell me what, where? I'm not sure I understand.
When we had the assembly with the call to the function still, could the value we're looking for been embedded somewhere statically there?
No, it wasn't. It wasn't. He didn't do it because it was the call to the function. He's not memorizing the function. He's really running them at compile time. It's not memorization.
Okay.
So no, the value I would not expect. You can check, right? You can do this yourself. You can check, but I'm pretty sure that if you look for that specific hexadecimal pattern, you're not going to find it anywhere. Yes?
So if you have a lot of values, like values that you don't know before compile time, and you want to like compute the color, say you take user input of the color, and you want to figure out the mapping, about the color.
That's what we'll do eventually, right? We're not there yet.
So does this work with the compile time?
Yeah, because what happens, that's the point of the lookup table, is that the runtime argument is the index into the lookup table.
Okay.
You pre-compute for all possible input, and then the input at runtime gives you the index into the table where you pick up the value.
So even in this case, it's making like.
Oh, in this case, I just computed one entry of the table. That's the only thing I've done. I've actually built up the machinery to evaluate one entry of the table. I don't have the table yet. We need to do more work to get there. Yes?
So you don't put like that, you don't like the time back 5 to load. The first time you run it, it might run slow, and the second time you run that same thing, it'll evaluate it in one time.
No. With the fact example, if we looked at this, right? I think I have it here, fact. Oh, which one? Fact MP, probably. I don't know if it's that one. Oh, this one is with the template. So that's with the const text. So maybe fact. No, that's still not the one. God, grab const text. Fact star. Fact 3. It's in fact 3. So when you write this in fact 3, right, written that way, if I compile that program and you look at the assembly code, because this thing is tagged const x, he will actually evaluate the whole thing at compile time, and all you will see in the code is what I showed you on the slide. You will see an assembly instruction that loads the constant 1 and 20 in a register.
Now, what if you wanted to build onto this program to allow the user to input a number afterwards?
Same idea, it's a lot. You define a lookup table and you say for all the input, you say user, you can ask me for any value of factorial between 0 and 100. You create a table, and in that table, you store at each entry the value of factorial for 0, for 1, for 2, for 3, for 5. When the user asks, give me factorial 12, you go at offset 12 in the table, you pick up the answer. You do a lookup table. That's what people in the gaming industry do all the time. Why do you think the executable in games are so big? Because they pre-compute everything. That's the only way to go fast, right? It's a good old-fashioned space-time trade-off. Pre-compute the answer, sneak them into the executable, and at runtime, you just pick up the answer. It's fast. Remember here, we just have the logic for computing one entry of the lookup. I still need to do the rest. I have another hour to go. We good? Everybody's with me? Convinced? Yes, Brandon.
I have a question about the lookup table. So
Yep.
let's say you didn't have integer keys.
I don't hear the integer, the keys are, well, I will make my table with integer keys, right? Because, well, I mean, that's the only way to build a table. You need to have integer keys. So here, the conversion is from a float, and the trick is to say, I discretize the input. I cannot ask for an arbitrary float value. I can only ask to values that correspond to pixel intensities, right? Because they're between 0 and 255. So I discretize. That's the only way you discretize. And if you want to have a finer discretization, make the lookup table bigger. Who's to stop you from making a table that's 65,000 entries? So that you are 16-bit precise. You pre-compute. It's a big table, right? 65,000 entries, 4 bytes per entries. That's a 250 kilobyte table. Sure, it's a big table, but it's accessed in constant time. Or one, actually one assembly level instruction. Yeah, sure, it will fill up your cache, but you shouldn't buy a Celeron in the first place. Buy a real processor that has real cache. Then you're fine. Why do gamers buy high-end machine? Because they need caches, because the programs are full of that stuff. Make sense? So yeah, you always have the flexibility when you discretize to make the table bigger. At some point, there is a trade-off, right? The quality is not good enough. But today, remember that most image manipulation programs are only 8 bits deep per channel. Few programs, Photoshop is one of the few ones. Pixelmator does it too. The GIMP still doesn't do it. They're all 8-bit per channel, but Pixelmator and Photoshop are 16-bit per channel. Just means a table that's 65,000. And it's the same table for all three, so it's okay. Make sense? So yes, to answer your question, what do you do? You all clear on this? Yes?
Little off topic, but
Oh, go ahead.
Do you think, have you ever noticed any difference between like Apple's C compiler and any other generic C compiler?
Yeah, I follow this. I follow this a little bit. The best C compiler out there is the Intel. If you care about performance, you pick the ICC compiler from Intel. It's actually free under some conditions, and you got to look for it. It's not. They don't publicize it very well because they consider it a reference implementation. So they don't advertise it. But that one is the one that generates the best code. The ones that you say Apple compiler is actually based on LLVM, which is a brand new implementation. If you take the compiler class with me, I would tell you all of this. But I'm not teaching it. Clang is really nice performance-wise. Apple has this habit, if you haven't noticed, of irritating all developers by making things not backward compatible. So they're perfectly happy removing things and breaking your code. And it has two consequences. Well, I'm going to make it short. It has two consequences. It drives programmers crazy because when the new version comes out, you have to go and edit your code to make it work on the new version. Anybody who's used Swift in that room knows that going from Swift 1 to 1.1 to 1.2 to 2 to 3 to 4 to 4.1, each time you edit your code, each time. They break it. What's good about it is that because they're willing to do that, they can remove the craft. They can remove the old stuff and make the code lean and mean. So that's why LLVM is going really well, and this is a good compiler. At the other end of the spectrum, you have the likes of Microsoft, where the idea is never remove anything, keep it backward compatible with the oldest we've ever entertained, which was a clone of VMS. And they do that for their APIs, their libraries, the compilers, for everything. So you have these monster compiler that can still, I mean, look at your Intel machine, right? It's the same story. Your Intel processor has remnants from the 1980s in the processor. Your processor boots in 16-bit mode and can only access 65 kilobytes of RAM at the beginning when it boots. Then it upgrades, goes to real, then protected, then the 64-bit mode that we use all the time. But it's the same story. Backward compatibility is a big thing. And they're slower to evolve, and because there is so much craft, typically they don't take advantage of newer architecture faster. So they're lagging a little bit behind. GCC is pretty good too. It's a good compiler. The others, I would be hard pressed to say. Some are terrible, right? But the companies that had really bad ones, they died. IRIX is gone. IRIX was a bad compiler, but it's gone, thankfully. I mean, they were great machines, the SGIs, but yeah, that was tough. So these days, Clang, Apple compiler, very good, but be ready, they break things on you when you change version. You have to port the code each time, which is a pain in the neck. Okay, that was an aside. Any other question on that stuff? Now we're good? Okay, cool. So let me go back. It's still recording. Okay, go back to the deck. This is where we are. Wonderful. We can now evaluate one entry of the lot. I still do not have my lookup table. So that's why I say, okay, I need to build, but this one is a little more difficult. Here I was calling a function that was spitting out one value. But with the lookup table, I need to build a data structure, a table, right? So how am I going to do that? Can I actually do this with const x? And of course, if I have another hour to go, you already know the answer. No, you can't do this with a const x. You're building a data structure. Const x is great, but it works only, it's one of its limitations, it works only on scalars. Integer, float, double, character, struct, arrays, then anything built on that, list, trees, and whatnot, forget it. Const x, scalar values only. But it got us some part of the way, right? I can now compute a single entry. Now I need to actually build my table. But we've seen a mechanism to do that, right? Just like factorial. Let's build types and stuck in type, the type everything we care about. And we'll build the table that way.
So you can't define like a static array of 256 cells?
That's what I'm going to do. but by actually using types to compute it. All right? That's what I do. It's just that I cannot write a function that's const x and returns to me a static array. That doesn't work. Because const x says you must evaluate to a scalar. And an array is not a scalar. So I cannot make a function that returns a static array. That won't make the cut. Right? Or I cannot have a function that has embedded in it a static array and just mark the function as const x and hope for the better. That doesn't work. I can't do that. Right? I really have to use that mechanism. Good. So let's go to the next place. And the idea is, okay, here we had, so this was a summary of what we did. Everything was evaluated at compile time. I just convinced you of that. So now let's do the second one, right? What's great is that I have something that works well. It will not be called if you're inside a context that's not const x, right? So the evaluation is only inside a constant context. And my colors, I need to convert them at runtime. So that's the point you made, one of you, right? That I need to make a lookup table where the index is the value I'm given at runtime, and the index is used to pick up the right value in the table that corresponds to the pre-computed output of the function. That's what I want to do. So that's my lot. So I need to construct it. And the trick is fairly straightforward, right? I'm going to actually use types to do this, exactly like in the example of the factorial. So I'm going to use these templates and these value templates where the template is parameterized by a scalar. Remember, in the factorial case, my template was taking an argument which was an int, was template int and struct fact, and then I have the value embedded in it. That's the trick I'm going to use. I'm going to use a template and use the value. So this technique of actually using a family of type that is parameterized by a scalar to actually pre-compute a bunch of value, that's what a trait is. Okay? And it's a type trait in general. C++ use them in quite a few places. So let me show you, that's the solution, by the way. So before we look at it, remember that what I want to have is an argument that's an index into the lookup table. Right? That's the position in the lookup table. I'm going to call it I in the code that's down there. Focus on both things. It's argument I that's the index in the lookup table. The value will be the result of the conversion according to the RGB or to the linear to sRGB conversion. Right? So that's the value I want to have. That's the value that will be embedded inside my type. So the argument of the type is the index of the value. The value inside the struct is the actual result of the computation. Now, how do I compute it? Well, I already know how to do that because I have my const x function. So now we have all the ingredients. The template indexed by the name of the value I wish to pre-compute. The function to compute the value. The place where to put it, which is a value embedded inside the type that corresponds to my trait. And that's it. So I'm defining here a constant. Of course, it's a macro, so it's at compile time. The size of my table 256. I'm creating a struct that I call LRGB, linear to RGB traits, LRGB trait, and it's templated by an integer index I. So that's my argument. That will be the index into the lookup. What it contains, no surprise, static const x float value. Right? It's a static, it's const. It's a const text because I want to have it evaluated at compile time, and I'm calling it value. And how do I initialize it? By calling real linear to sRGB, I take my index, which is between 0 and 255, and I divide it by the size of the table, and lo and behold, that gives me my color range. Right? It gives me an intensity which is between 0 and 1, which is what I feed to real linear to sRGB, which is, of course, a const text. So a const text stored into a const text, exactly as in the example I've shown with you a second ago, that would create me an instance of LRGB trait with the value pre-computed. I can even use a version of assert, which is kind of neat. It's called static assert. This assert is not an assert that will run in debug mode at runtime. It's an assert that runs at compile time. It's an assert that verifies that the result of the computation that happened at compile time is correct. So here I'm asking to the compiler, please check yourself. If I were to create an LRGB trait for the index 1, right? It is the second entry in the table. Its value should be about 0.049669. And I'm checking this by saying that the subtraction between the two should be less than a very small epsilon. If this static assert passes, it means that the compiler successfully generated this type that has this value embedded inside that correspond to the pre-computed color conversion for the entry 1 of the table. Are you with me? What am I missing now?
Similar to call that.
Yeah, so the table, right? I mean, the problem is that this gives me one value. Now I have a way to embed one value of interest inside the type. I don't have the table yet, right? I still need to do the table, but at least now I've converted from the const x mechanics to actually embedding the value in the type. Now if I want to build the actual table, where is that table going to be from the compiler standpoint? When I'm doing metaprogramming, where are values stored? Inside types. Yes, that's what I was looking for. Right? Values are embedded in types. Here I'm putting one entry of the lookup table in a type, LRGB tray 1. Now I want to build a type that will contain the whole table. Right? That's the whole idea. Build a type that contains the table. Now you have a type that contains one value of the table. Okay? Cool. We're on our way. We're a lot closer than you imagine. We'll have actually time to properly discuss this at length. So that's the next thing I want to do. I want to head into this meta-programming to actually build the entire table itself. Now, you realize, being a table, it has, in this case, 256 indices between 0 and 255, right? So it's a type that contains like 256 frames. Do you want to call by hand like that each time and type LRGB tray 1, LRGB tray 2, LRGB tray 3, LRGB tray 4? It's painful, right? Because if I ask you, oh yeah, but you do that. Imagine you do that 255 times. Then you show to your boss, oh, I have it. It's like I have roulette and everything. No, everything's constant time. Then your boss says, oh yeah, I'm sorry. Like the art department finds the picture crappy. They want you to go to 16-bit color accuracy. What do you do? Reject answer. Now, of course, if you have typed this thing 255 times, Oliver is trying to be smart here, right? He's trying to like, oh, you did it 255 times. Use the stream editor to do it 65,000 times. If you don't know about SED, you're like crying and you go behind your laptop and you start typing 65,000 times. Control X, Control P, Control X, Control P, Control X, and you copy paste that line 65,000 times. If you make a bug anywhere, you're going to reproduce that bug 65,000 times. Is that sensible? No, of course not, right? You don't want to do that. You don't want to use SED, even if you're smart, too much for your own good. You don't want to do that. Or you don't want to type everything by hand. You want actually to write a program that does that, and you still want, because yeah, you know that C++ is Turing complete as a compiler. You can compute anything you want. That's what we want to do. Well, I mean, that's the problem. If you write the for loop, when does the for loop run? It runs at runtime. We want to do everything at compile time. So we can't have a normal for loop. We have to embed that in the types. That's the trick. So we got to do something like that. There won't be for loops.
So is it just declaring the structure at the value 1 that computes it?
No, it's declaring a type. Remember, LRGB tray is a structure. It's defining a type within the family, because this is a whole family. I could pass, as an index, I could pass 32,762 if I wanted to. So it's defining one instance of the type within the family. What I'm saying is that to define a table with 16-bit precision, I would need to create 65,000 of these types from the family. And that's not something I want to type by hand. Here I typed one of them by hand. I could support that. I don't want to do that by hand. Right? I really want to create all of them programmatically. Okay? Right.
But so you said you couldn't do a for loop. Why can't you put a for loop inside a constant expression function and call that constant
So if I make a for loop, right, when is the for loop going to run? Because it's going it's going to run at runtime, right? Even if you put everything as const text for the for loop itself, it would create an object that normally is valid for the iteration and would get rid of the type. I have the value, I need to pick up the value that's in the type and do something with it.
Wait, so
You know what? I
so you
understand
can't do-
completely your point. That's why we need a homework. Because this is a lesson that's really tough to make sing, is when are things done? And if you think about what you do with a for loop, if you had a for loop and inside the for loop you have an LRGB tray with an index that corresponds to the for loop, what you're seeing is that the index depends, the value you pass here depends on the index of the loop. So even if he unfolds the loop, he's going to create that, pick up the value, and then what does he do with it? What do you do with the value? Where do you put it?
So with a template, doesn't your C++ compiler go through and figure out all the different
It creates the types.
polymorphisms that like
Yeah.
So if you do a for loop and mark the function with constant expression, would it run that for loop back to problem?
Oh, yeah. At compile time, it would run the for loop, right? So it creates all these types. Then what do you do with that?
What if inside that for loop you have create those constant expression LGBR?
Yeah, you create that thing.
traits, right? What if it?
So
and
you're
then
arguing
copies-
for C++ to support const exp over arrays. I agree with you, it could be done. I'm not saying it's impossible, right? Remember that this is not about whether it's doable to extend const exp to support the creation and filling of array structure. It's just that const exp in the C++ 14 and 17 version of the standard does not work on anything other than scalars. You're asking to go and index an array at compile time and just it's telling you, like, I'm not going to do this. It will generate runtime structure instead. You cannot in C++ create arrays via const exp. What you're trying to do is exactly that, which is a sensible thing to do, right? And maybe that's what Jai does. I haven't checked close enough. Maybe that's doable. C++ doesn't allow it. It has a different mechanism, which is computing with types, for actually doing things that are arbitrary. And that's what I'm showing you here, that you can do it that way. What you want to do, maybe C++ 23 will be able to do that. I'd love it because the const exp stuff is really readable, right? What I'm going to show you is a little more hairy, but it works today.
I figured I would just comment on what Jai does. Like whenever it gets like the run directive, which tells it to run a piece of code at compile time, it compiles all the necessary code that it would need to run it into a bytecode, and then executes that bytecode at compile time. So then you're actually not limited by anything. You could do side effects code. You could call syscalls. You could do anything.
Yeah, which is why I suspect that you can, I'm pretty sure you could do const exp with arbitrary types, which is like C++ didn't support that. Right now it's not in the standard. Right? C++ is one of these languages that's always backward compatible, going back to the earlier one. C++ always is backward compatible. They don't break anything. So they will, next version of the standard, part of the discussion is that they want to preserve performance while authorizing to do that kind of stuff. I mean, I think they should get to it because it would be very elegant to just have a const exp that spits out an array and then we'd be done, right? Right now it's not possible, so I'm showing you what can be done. One in the back menu.
Why don't you just add one more line in the LVDR thing that computes the LRGB of 1 less than I, and then when it goes back in, it'll.
That's what we're gonna do. You are guessing where we're going. That's where we're going.
I'm good.
You're good?
Sorry.
All right. Good. So I think that you're starting to get the gist of where this is heading, right? So we could do it for one. So now let's do it for multiple. So